Hello everyone, good morning. We're going to actually begin day 3 and we're going to wrap up 11.1. And so we're going to do the last day, and today you're going to be able to model with power functions. So let's take a look at these problems, and we may be relating to some real world situations as power functions. So basically a power function is written in the form of y equals a x to the b. And where a is a real number and b is a rational number. So can be a fraction. So b is going to be a fraction. And so we're giving you some review for the formulas, the area of a circle and the volume of a sphere. Hopefully these formulas look familiar to you because we're going to be applying them when we are working with the problems today. And here's number 1. The function h of m equals 241 times m to the negative 1/4 models an animal's approximate resting heart rate h in beats per minute given its mass m milligrams. And part A says a common shrew has a mass of only about 0.01 kilogram. To the nearest 10, what is the model's estimate for this shrew's resting heart rate? So as you know, or maybe you don't know, maybe you do know, a common shrew is basically just a type of mouse. So it's pretty small. It may be able to fit on the palm of your hands. So the weight is rather small. So if we're going to just substitute the mass, because the mass is given, right, in this case. So we're going to substitute h of 0.01 into the given function. That's equal to 241 times 0.01 to the negative 1/4 power. And if you work it all out, hopefully you know how to apply this in your calculator and obtain the answer. You should have an approximate 762.10, or it says estimate to the nearest 10, which means the n should be 0. So it's about 760 beats per minute. So go ahead and test out your calculator to make sure that you're getting this answer in your calculator, so you know how to work with your calculator, raising these powers on your calculator. Next, part B says, what is the model's estimate for the resting heart rate of an American elk with a mass of 300 kilograms? So as you know, the elk is a lot bigger than the mouse, so therefore it's a 300 kilogram. That's about like 600 something pounds. That's pretty heavy. So what is the heartbeat of this big, large animal? So we're going to again apply the mass, which is now 300, into the formula that's given. So it's 241 times 300 to the negative 1/4. And again, applying that in your calculator, you should have 57.91, approximately 60 beats per minute. So as you know, what conclusion can we draw here? The smaller the animal, the higher the heartbeat, right? The bigger the animal, the slower the heartbeat. And part C says two animal species differ in mass by a multiple of 10. According to the model, about what percent of the smaller animal's heart rate would you expect the larger animal's heart rate to be? So if we let 1 represent the mass of the smaller animal, then we're using the formula, the same formula that is given, 241. Then the larger animal is going to be, so this is the larger one. This is going to be the smaller one. So it's 241. Then 10 times means 10. So the larger animal is going to have a weight of 10 times, right? So if we just let the smaller one weight is 1, then the larger one is going to be 10. And same formula here. And we just do the math and divide. You should have 0.56 as an answer, or expressed it as 56%. So you would expect the larger animal's resting heart rate to be about 56% of the smaller animal's rate. So larger animal HR, heart rate, is 56% of smaller animal. That's the conclusion. Okay? And next problem says in every atom, electrons orbits the nucleus of a certain characteristic velocity known as the Fermi-Thomas velocity, equal to this expression right here, where z is the number of protons in the nucleus and c is the speed of light. In terms of c, what is the characteristic Fermi-Thomas velocity of the electron in uranium for the z is equal to 92. So for uranium, they're giving you that z equals 92. So we're just going to straight plug in 92 for z into the formula and raise that to the 2/3 power over 137. And basically, we are just going to simplify this entire coefficient right here. And you can work it out with the calculator, and it actually should be 0.15 c. And now this is the new expression that represents the Fermi-Thomas velocity for uranium. And here's a discussion problem. What is the difference between power function and an exponential function? So a power function is when you have something like y equals 2x squared. But like, so the power is actually like a number, like a polynomial, right? For anything that has higher than 1. And then an exponential function is something like y equals 2 to the x, where the x is the variable, like the power is actually a variable. So that would be the difference between a power function and exponential function. Hopefully that clarifies things. And that is a wrap for module 11.1, lesson 11.1. So hopefully you guys understand how to operate with the radical and rational exponents and how to apply it to daily problems. And have a wonderful day. Go ahead and log into Google Classroom to find out what is your homework. Bye.